Okay, this is lesson 1.4, domain and range. Something we've already kind of visited in the first lesson. Just to review, domain is all the possible values of x, and we can write that as a set just by listing all the possible values. But if that list is too extensive, we can use set builder notation. Range is just all the possible values of y. To determine domain and range, again, we can use set or set builder. One thing we need to do is if we have an equation, we need to consider what the parent function looks like and then any sort of transformations that we may have there. As we look at transformations, we'll get better and better at working just from an equation. But for now, we can either sketch the graph or we can think about what values we can actually put in a domain and what values we can get out for a range. And we're going to kind of try to do that today. And then secondly, if we have a word problem and that word problem is about perimeter or area, we need to think about like natural restrictions. So for example, we can only have positive area. So if we're looking for the range of an area question, we need to only consider areas that are bigger than or equal to 0. You can have 0 area, but you can't have -1 area. You could have 5 as an area, but you can't have a negative. So we need to restrict the range in that way. And we'll see an example of that when we do the back page. So let's start. Let's start with just a graph. Graphs are generally the easiest ones to write domain and range for. So let's try the domain here. The domain of this graph. Well, what we have here is we have a bunch of points. They're not connected with a line, so we're not talking about real numbers in this case. We're just talking about the individual values of these points. And if we're looking at domain, we're talking about the x's. So on the x scale, we've got -3 leads to a point, -2 leads to a point, -1 gives us that point, 0, 1, 2, and 3. All those values of x give us a point. So all those values of x are in the domain. So the easiest way to write this would be just listing them. -3, -2, -1, 0, 1, 2, and 3. And that's a pretty big domain. Or we could say, hey, those are just integers. No decimals, no fractions. They're not real numbers. Well, they are real numbers, but they don't include anything between them. So we go with the smallest set possible, and that's integers. So we could say, hey, well, let's use set builder notation. And let's say that x belongs to integers. And we got a z with that funky double line in the middle, such that the smallest x here is -3. So -3 less than or equal to x. And if we read from the middle, x is greater than or equal to -3. Less than or equal to 3 is the biggest. And we can close the set. So this is our domain using set builder notation, and this is our domain using set notation. So I'll let you try the range. Try to write the range using set notation and set builder notation, and it's done pretty similarly to how we did the domain. Let's try B. B, we have a circle, and this circle has a radius of 5. If you look from the center, 0, 0, all the way out, 5 is the max, and 5 up here, and -5 all the way over here, and -5 all the way down here. So this circle is between the 5s. So when we write our domain, we need to say, hey, this circle exists all the way from -5, and it goes all the way to 5. That x scale is filled in all the way in between. And since we're connected with a nice smooth curve, we're using real numbers. So we can't just list points because we have an infinite number of points to make that smooth curve. So we can't list points using set notation. We have to use set builder. So we have to say, okay, since we're connected with a nice curve, x belongs to real. And then we have to think about the smallest x. So I'm going to say x greater than, less than. The smallest number of x is -5. And it actually touches -5, so we're going to say equals to as well. And the biggest x is 5. And it touches 5, so we're going to say equals to as well, and then we can close our set. So there's our domain. X exists between -5 and 5, and it's all real numbers between -5 and 5. And I'll leave the range for you. See if you can write the range. Okay, let's try some equations. Equations are the trickiest ones to write domain and range for because you don't have a picture. Sometimes it's easy to come up with the picture, like this one. F of x equals x plus 4. That's a line. If we think about what that line looks like, in a sketch it here. That's the axis, it's not the line. This has a y-intercept of 4 and a slope of 1, so I'm just going to approximate here and say, boom, there's my line. There's f of x, and it goes through 4. So let's think. Are there any restrictions on x? Well, no, because it continues all the way to the left, all the way to the right, and everything in between. So for a domain, that's just x belongs to real. And when we did our parent functions last lesson, the line had no restrictions on the domain, and in fact, it had no restrictions on the range either. That one's not too bad. D is a little trickier. D is the square root function. And since we haven't worked much with transformations, we're not going to sketch this using transformations. We're going to think about this one logically and try to reason out the domain. So what do we know about a square root? Well, what we know about the square root is that you can't take the square root of a negative number. So we have to ask ourselves, what numbers could we put in for x that would give us a negative? If we put 0 in for x, we have 2 minus 0, and you can take the square root of 2 and get an answer. So 0 is okay in the domain. 0 is a fine x. If you put in 1, you got 2 minus 1, which is 1, and you can square root 1. So that one's fine too. It's when you put in 2 and numbers bigger than 2 that we have to start to ask ourselves some questions. If we put 2 in for x, if 2 is in the domain, 2 minus 2 is 0. Can you take the square root of 0? Yes, you can. So 2 is okay. But anything bigger than 2, if we did like 3, 2 minus 3 is negative 1, and you cannot square root negative 1. You get an error. So negative 3 is 3 is not in the domain. 2 was, but 3 is not. So we have some sort of disconnect there. Let's try a number closer to 2. Let's try 2.1. If we did 2 minus 2.1, we'd get negative 0.1. And negative 0.1 you can't square root, again, because it's negative. So really, the problem here is that x can't be anything bigger than 2. And figuring out that is figuring out the restriction, and that helps you write the domain. So here we go. Since the parent function is the square root of x, and the square root of x has a restriction, and it continues, let's graph it instead of just talking generally. Let's give you a picture. From yesterday, the parent function. Since it's the square root, we know the graph looks like this. This is y equals the square root of x. And this is some sort of transformation that we'll get into later in the course, in the unit actually, later in the unit. Something's happened to this graph, and the original started at a point and continued forever. So we know that x belongs to real, and the key to finding the domain is figuring out what that restriction was, and I think we figured it out. We figured out that x can't be a number bigger than 2. So that means that x has to be less than 2. That's the restriction. X has to be less than 2. Can it be 2? Yes, because 2 leads you to 0, so it can be 2. So that's our domain. For the range, you have to think about what answers you get after you square root a number. Can you get a negative answer when you square root a number? No, you can't. You can only get positives. Can you get 0 when you square root a number? Yes, you can. Because if you square rooted when you put in 2, 2 minus 2 is 0, square root of 0 is 0. So for the range, y belongs to real, but y has to be greater than or equal to 0. Writing the domain and range of something that you don't know how to do the transformations of yet, a little tricky. But thinking about what can go in is the domain. And thinking about what answers you can get out is the range. So we'll do a little bit more practice with that, but once we can actually transform that graph, domain and range of these functions are going to become much easier. Let's flip back to ones you're more familiar with. Parabolas. I'll do one and you'll try one on your own. I'll do the left one. Let's think about what the left one would look like. Well, we know it's in vertex form, so let's try to do a sketch. We don't need a perfect graph, we just need a sketch. The vertex of this would be negative 1 and 6. So I'm going to plot a point up here and we'll say that's negative 1, 6. And it's going to open down, and that's key. 6 is the max, and it's going to open down. So our parabola is going to look something like this. And that sketch is enough for you to write the domain and range. Why? Well, think about the domain. It continues all the way to the left, all the way to the right, and everything in the middle on the x scale. So x belongs to real. And what you saw yesterday when you did parent functions is that the parabola, y equals x squared parent function, doesn't have any restrictions on the domain. It does have a restriction on the range. We know that it has to either be above or below the vertex. And in this case, the vertex is 6, and it only exists below the vertex. So for our range, y belongs to real, and y has to be less than, below, 6. But it can be equal to 6, so we have to include that. So y has to be less than or equal to 6, and that makes sense because that's the maximum point. Okay, you can try f by sketching a graph and then writing the domain and range. Let's flip the page. Example 2. We're going to do this example in the video, and we're also going to do one similar tomorrow in class. A farmer has 24 meters of fencing to enclose a rectangular garden at the back of her barn. She will use the barn as one wall of the fence. Express the area of the garden as a function of its width. So let's try to draw this. We've got a barn. I'm quite the artist. Barn. And we're going to make a rectangular garden. Rectangle. Here's my garden. I'm not going to write garden because that's a big word in a small space. What do we have here? Well, we could call either of these the length or the width. Usually the long one's length. So we got length, width, width. And express the area of the garden as a function of its width. So we need to define some of our variables here. We've got W. So we're going to say let W represent the width. And we want to write the area as a function of width, so we need to define A for area. Let A represent area. And if we want to write an equation for area as a function of its width, we need to write A of W. And how do you find the area of a rectangle? Well, you do length times width. So L times W. But we have a problem here. And the problem is when you have a function of something, function of width, you can't have other variables on the other side. You can only have W's. So we have to figure out how to replace this L with something with respect to width, and that's where this part comes in. Farmer has 24 meters of fencing. So that means that the two widths and the length must add up to 24. So we can write a little equation off to the side here and say that the perimeter of this has to be 24, and the perimeter of this is only 3 sides, and it's made up of 2 widths plus a length. And if we isolate for L, we get 24 minus 2W. And now what we can do is we can replace the L in our area equation with 24 minus 2W. And we get this. And now what you have is you have an area equation with only W's. And now you have the area of a garden as a function of its width. So what do we want to do here? Well, this is in a factored form because it's in brackets. If we expand it, we can get it in standard form. So I'm going to do that as one last step. Negative 2W times W would be negative 2W squared, and 24 times W would be 24W. And that's A. Express the area of a garden as a function of width. B asks us to determine the domain and range of the area function. We want to find the domain and range of this parabola. And let's think about what this means. This means that we want to find the domain and range of a parabola. How did we do that earlier? I'm just going to flip back here. When we wanted to find the domain and range of a parabola, we sketched it. And the domain was x belongs to real. No restrictions on x. We're going to reconsider that when we do this graph. And the range was less than the vertex. So we need to find the vertex, because either it's going to be less than the vertex because it opens down, or it's going to be greater than the vertex because it opens up. So we need to go and consider where the vertex is. So let's go back. We have a quadratic equation. It's a parabola, and it opens down because it's negative. So we need to find the vertex, and our range is going to be less than the vertex. Let's think about first restrictions on width, because we can probably do this one right now, the domain. The domain, the x's, right now we have w's in the place of x's, so our domain is in terms of width. So what are some restrictions on the width? Well, width can be any number within some certain conditions. We have to think logically. If we have 24 meters of fencing to enclose a rectangular area, what could our width be? Could we have no width and just put all the area for length? Well, we could, but then we wouldn't have a rectangular enclosure. So we can't have widths of 0, but we can have widths slightly bigger than 0, like 0.1 meters. And if we have that, then we could build a rectangle. So what we know is that the width has to be greater than 0. It can't be equal to 0, or else we wouldn't have a rectangle. And if we have 24 meters of fencing, how much could we put for each width and still have enough to build a length? Well, if we did 12 and 12, we would have 0 remaining for the length. So we'd have to have slightly less than 12. So less than 12. So widths has to be some number between 0 and 12. And this restriction on width is because we only have 24 meters of fencing. To find the range, we actually have to figure out the vertex. How do we find the vertex of a quadratic? That's something we practiced in the review unit. We have to complete the square. So, negative 2w squared plus 24w. Alternatively, you could factor, find the x-intercepts, and then use the axis of symmetry to find the vertex. But we're going to complete the square. Group the first two terms. There are only two terms. Common factor the negative 2. Take the negative 12, divide it by 2, and square it. If we divide it by 2, we get 6. If we square it, we get 36. Bring the negative 36 out. Negative 36 times negative 2 is 72. And now we have to factor our quadratic in the middle. Square root of the first term gives us w. Half the middle term gives you negative 6. And we have vertex form. So what is our vertex? Well, our vertex would be 672. What's that represent? Well, it represents the maximum area. The maximum area is 72. And the max area occurs when we have a width of 6 meters. So if the width's 6 meters, we get a max area of 72 meters squared. So what's this all mean? Well, let's graph it, and it might help. I'm only going to use this part of the Cartesian plane because we're talking about area and we're talking about width. So what do we know about width? Well, width has to be between 0 and 12. So not including, so we're going to use open circles. Here's 0 and 12. 0, 12. And we know the max occurs at 6, right in the middle, which kind of makes sense. If those are the restrictions, 0 and 12, the middle must be 6. And the max area is 72. So we have a parabola that opens down, has a max of 72, comes back down and hits 12. So there's a picture of what our area does. When the width is slightly above 0, we have a really small area. And when we get to 6, we have a big area, a maximum area, and as the width gets bigger, our area goes down. How does that help us write a range? Well, the range is about areas. The area with respect to width belongs to real numbers. It can be any number between 0 and 72. Not including 0? It is including 0. That's a little tricky. No, it's not including 0 because we don't have a 0 width or a 0 length. So we have a restriction there. So area has to be bigger than 0, but less than or equal to 72, because we can equal the maximum, and we do that when the width is 6. All right, tricky question, but we're going to do one similar tomorrow in class. Thanks for watching, and I'll see you next time.